Hi, my name is Mihika Dusad, and I go to Thomas Jefferson High School for Science and Technology in Alexandria, Virginia.
Hi, my name is Sashwat Ravishankar, and I go to Jesuit High School in Portland, Oregon.
And my name is Danielle Sitalo, and I go to DeBakey High School for Health Professions in Houston, Texas.
When we first read Problem B, we were instantly captivated. According to the Problem B Punishing Infants problem statement, research shows that some infants develop a propensity to react to third-party transgressions by punishing those they perceive as acting out against others. We will refer to this as the propensity for retribution. We are told to assume that the proportion of infants that have this propensity is fixed, and the objective then is to study interactions between third-party individuals observing conflicts and the long-term dynamics of the system as a whole.
Now, I want to talk about some of the goals that we employed throughout our project. And the first of four goals was that we wanted to develop a model that included multiple populations with different characteristics and different propensities of retribution for that third party. Our second goal was that each of these populations would employ a different behavior. That way we could look at cases with the third party choosing harsh retribution versus maybe a milder course of action. The third goal was to study the long-term effects of the model's interaction. And finally, we wanted to generalize and apply our model to real-world scenarios that are occurring in our modern society today.
Here are some definitions that are used throughout our model. Firstly, the propensity of retribution is the likelihood of an observer to punish a third-party aggressor. Furthermore, the propensity to aggress is the likelihood of every party to commit aggressions. And in our model, an individual can take one of three roles at any given moment. Firstly, the observer or bystander role, in which they are observing a conflict take place. The victim role, in which they are currently being aggressed or attacked. And lastly, the aggressor role, in which they are the ones currently aggressing against the victim.
For this problem, we made some assumptions to simplify the model. We assumed population beliefs and distributions for a group or party are uniform. We assumed there is always at least one going conflict or instance of aggression. We assumed individuals can only be involved in one conflict at a time, and we determined that actions should be cyclical, meaning individuals can always cease action or move back to a previous course of action through some number of steps. Lastly, we assumed linear progression between the states of involvement in conflict. This movement between roles suggested the efficacy of an SIR model, which we will further explain.
The SIR model, or Susceptible Infectious Recovered Model of Epidemiology, is a fundamental mathematical framework developed by Cormack and McKendrick to study the spread of infectious diseases within a population. By analyzing the interaction between the three compartments S, I, and R, we're able to gain insights into the progression of a disease's contagiousness, as well as the potential impact of interventions. Now, we decided to apply this infectious disease model to our problem statement in a victim aggression context, where the SIR model is used to represent international conflict between two countries, where there's a third-party country that chooses to either engage or not engage in pursuing a course of diplomacy for this conflict. So this is a quick breakdown of the model framework that we developed. The S here is susceptible, and the susceptible population is any countries that are aware of ongoing conflict. Now, when you move to I, infected, the countries are actually involved in that ongoing conflict. And then we have our 3D stages. The first base one is diplomatic. So this means that a country decides to pursue some course of action. And then you have D1 and D2, which further the complexity, where a country pursues a mild course of action, such as a sanction or a treaty to address the conflict, versus D2, where a country pursues a harsh course of action, such as warmed or armed attacks to address the conflict. And finally, we have R, which is our recovered population, and that would be any country that stops pursuing a course of action between the two countries that are in conflict. So in stage one of our model, this is our base level, we're looking at S, I, D, and R. So we're not looking into how severe or the propensity of retribution, but simply whether a country decides to pursue a course of retribution within the conflict. One important thing to note here is that between the I and D compartments, we have alpha and zeta, which indicate that a country can move back and forth between pursuing a course of action or deciding not to. In stage 2 of our model, we bring in the propensity of retribution with D1 and D2. And predominantly the terms alpha and zeta here again describe the rate at which a country pursues a harsh course of action versus the rate at which they pursue a milder course of action. Both of these then do flow into the recovered compartment, and countries are able to become resusceptible to another source of conflict that is occurring. In both models, we employed 5 differential equations to understand the rate at which individuals and countries are moving from compartment to compartment.
For stage 1 of our model, we conducted stability analysis to determine the long-term behavior. Stability analysis is the systematic evaluation of the behavior of a system to determine whether it remains within the desired bounds under various conditions and is crucial to ensure the reliability and predictability of systems, preventing unexpected or undesirable behaviors. Solving for the equilibrium solution, we obtain this set of equations, in which the equilibrium solution is asymptotically stable as t goes to infinity for all positive values for the rates alpha, beta, gamma, sigma, and zeta. Here is a visualization of stability analysis.
Next, we undertook hyperparameter tuning, a technique that uses data to optimize model parameters. We first obtained data from the Global Sanctions database, and as can be seen in the image to the right, this data includes information on sanctions since 1949, and it lists objective and success for each sanction. We numerically scaled these objective and success values such that objective could be used to represent the propensity for retribution, and success was ranked on a 5-point scale. Averaging out over all 1,325 data points, we calculated that the centroid was located at approximately 6.793, 3.04. This indicates that countries tend to have harsher retributive tendencies, but they result in average outcomes of success. Using this in our findings, we were able to investigate specific cases.
Now, after completing the model and conducting the stability analysis and hyperparameter tuning, we wanted to apply this to a real-world scenario. Of course, there's been the unfortunate recent conflict between Israel and Hamas, where the USA has been serving as a third party, and currently they've been pursuing a mild course of diplomatic action. And hence, we decided to make the alpha parameter, which is mild diplomacy, much higher weighted than the zeta parameter for a harsher course of diplomacy. We then conducted 2 simulations, one over a 10-day period and one over a 60-day period, to assess both the short-term effects and the long-term effects. In both simulations, we found that the infected population, as denoted by the orange line, dies out really quickly, which depicts the urge of a third party to take some course of action. Additionally, in the long term, it's clear that the D1 parameter and population is much greater than the D2 population. So although there are countries that are moving back into being susceptible to conflict, those countries that pursue a milder course of action tend to have a larger population throughout the conflict. What this tells us is that if the US does continue to pursue a mild course of diplomacy, such as sanctions or treaties, rather than pursuing war or armed conflict, the recovered population will continue to grow, as denoted by the purple line for recovery.
The second case study we looked at is the Russia-Ukraine conflict, in which the US has been pursuing a more harsh retributive course of action. We accordingly set zeta to be weighted higher than alpha, and in the 2 images, these were our findings over a 10-day and 60-day simulation period. In the long term, we see that D2 has a higher population than D1, but the recovered population is smaller than in the first case study, which makes sense because more countries have ended their involvement in the conflict.
In conclusion, we were able to create an SIR-based model of the punishing inference problem that is complex and incorporates varying degrees of retributive behavior. By stabilizing and tuning both the D1 and D2 compartments, we were also able to analyze the propensity of a third party's courses of action. Some limitations of our model are that we only consider one conflict at a time. Movement between compartments is restricted to linear movements, and the likelihood of aggression is not considered when a conflict begins. For future work, we would try to include additional variables that enable back and forth population movement to a greater extent, as well as considering environmental factors that could influence conflict. Here are our references. Thank you very much for listening.